In this lecture, we will be introducing the concept of three-dimensional real space, also known as R3. So thus far, you're used to working in two dimensions, where you have an x-axis and a y-axis, and we now add one more axis, and so we will have x, y, and z axes. And we call this a right-handed coordinate system. And we call it a right-handed coordinate system because if you take your right hand and you point your index finger in the direction of the positive x-axis, and then you curl the rest of your fingers to make a fist, then your thumb will point in the direction of the positive z-axis, and these other fingers will point in the direction of the positive y-axis. That's why we call it, again, a right-handed coordinate system. Now, three-dimensional space, when we divide it up into different sectors, let's think about what we did in two-dimensional space. In the xy plane, we had 4 quadrants, and we named them in the following fashion, in this counterclockwise manner, where the first quadrant was the sector where all points have positive and negative x and y coordinates. In three-dimensional space, we have 8 octants. So when you add a z-axis, think coming out of the board here, you basically have 2 octants spawned for each of the 4 quadrants, one below and one above. So we have octants. And unlike the xy plane, where we name each quadrant, we actually don't name the octants except for the first octant. So the first octant, that would be described as the set of points x, y, and z, such that the x, y, and z coordinates are all greater than or equal to 0. And that, as depicted here, would be our first octant. And if we wanted to see axes that have all the octants, we would look at something like this. And you can see here that you would have 8 octants. When we talk about points in three-dimensional space, we want to look at the distance between them. And so in this case, suppose we have these 2 points, P1 and P2. So here would be P1, and we can say that we would have x coordinate x1, y coordinate y1, and z coordinate z1, and then our other point, P2, has its coordinates x2, y2, and z2. And the distance between them we call it d, is given by this distance formula, which is the Euclidean distance between the 2 points. So we take the differences of the components, we square those, add them, and take the square root. For example, suppose we want to find the distance between these 2 points, the point A, 147, and B, 226. Using our formula, we would say that distance d is the square root of, so let's take the difference of the x coordinates and square them. So 2 minus 1. Then we add the difference of the y coordinates squared, 2 minus 4. And then we add the difference of the z coordinates squared, 6 minus 7. So we get the square root of, here we have 2 minus 1, or 1 squared. Here we have negative 2 squared. And then we have minus 1 squared, for an answer of the square root of 1 plus 4 plus 1, or root 6. And if we wanted to see what this looks like, in this case, A is at the point 1, 4, and then up 7. So this would be our point A. And B is at the point 2, 2, 6. And we have just seen that the distance between them, depicted in lavender here, is root 6. And so this is what our picture looks like. This is the distance that we just computed. And note that it's a good idea to get into the habit of drawing these things. Part of dealing with multivariable calculus is dealing with drawing things in 3 dimensions, and it's an important skill to practice. It's especially important to not become overly reliant on technology, like software or using a graphing calculator. Those kinds of things are helpful, and they can be used as supplements, but they should not be used as a primary method for looking at these things. It becomes important to be able to imagine them and picture them yourself. To get a little bit more of a feel for working in 3-dimensional space, let's think about the example of a sphere. And a sphere is just a natural extrapolation of the concept of a circle to 3 dimensions. So given a point C with coordinates HKL in R3 and in R greater than 0, the sphere with center C and radius R is defined as the set of all points P in 3-dimensional real space, such that the distance from P to C is R, the radius. The way you would imagine a sphere, if we now put our X, Y, Z axes in play, and the center is the point C, and then a point on the surface of the sphere is P, this distance between the two should be R. So that distance R is the length of that line segment CP, and the length of that line segment CP is the distance between the point C at the center and the point P on the surface, which by definition is the distance between the 2 points P and C. So we can take the difference, using our previous slide, we can take the difference of the coordinates, square them, and add them up. So we would have x minus h squared plus y minus k squared plus z minus l squared. And then you see, if you square both sides here, we recover this equation labeled 2 here. And you also see that this is a natural extension of the equation of a circle. if we didn't have, in R2, if we didn't have this term here, this would be the equation of a circle in the xy plane with center HK. For example, let's consider this equation here, and let's see how it actually is in fact the equation of a sphere. In order to do that, we need to write this in the form that we had here in equation 2. We need to identify the center. And we can do that by completing the square in x and in y and in z. So recall, for completing the square, you need to identify your terms that are usually labeled as b. So in this case, our b term would be, for the completing the square in x, minus 8. Our b2 term for completing the square in y would be minus 9. And our b3 term for completing the square in z would be 10. And so to complete the square, we add each of those b's squared over 4 to each side. So for I equals 1, 2, and 3. So doing so, we have our completing the square in x. So we have x squared minus 8x. So our b1 was minus 8. So minus 8 squared is 64. Over 4 is 16. So we add 16. To complete the square in y, we have plus y squared minus 9y minus 9 squared, 81 over 4. And then we complete the square in z, and we get plus z squared plus 10z plus our b3, which is 10. We square that, which is 100, over 4, which is 25. And that equals, now we have to add these same terms to the right-hand side to, of course, maintain the equality. And so this is equal to 16 plus 81 over 4 plus 25 and minus 40, remembering that we have to account for this minus 40, this 40 on the left side here. Simplifying that right-hand side, 25 minus 40 is negative 15. Negative 15 plus 16 is 1. So this is 1 plus 81 over 4, or 85 over 4. And on the left, we now take advantage of the fact that we have completed the square. And so we get, for the x-coordinate, x minus 4 quantity squared. For the y-coordinate, we have y minus 9 over 2 quantity squared. And for the z-coordinate, we have z minus 5 quantity squared. And so we see this equals 85 over 4. So we now have this equation which identifies as the sphere of radius root 85 over 4, or root 85 divided by 2, centered at the point 4, 9/2, 5. Now that we have introduced three-dimensional space, we want to start to think about vectors in three-dimensional space. And vectors in three-dimensional space are a natural extension of vectors in two-dimensional space. So for example, if we have the point P in R3, and it has coordinates A, B, C, then the vector V is the position vector for P when we define it with coordinates A, B, C. So you can think of it as the vector pointing from the origin to the point P. If we want to find the vector between 2 points, A and B, in R3, so if you have your point A and you have your point B, and you want to find the vector going from A to B, and it's important to note that it's directed. We write this as the vector starting at the point A and ending at the point B. Then we take the vector of the differences of the respective coordinates. So we take the first coordinate of the endpoint and subtract the first coordinate of the beginning point. Then for the x-coordinate, for the y-coordinate, we take the y-coordinate of the ending point minus the y-coordinate of the beginning point. And then we do the same for the z-coordinate. And that gives us the vector from the point A to the point B. For example, suppose we want to find the vector from the point A, 147, to the point A, 226. Our vector AB will be the vector where, again, take the x-coordinate for the end point and subtract the x-coordinate for the beginning point. 2 minus 1. For the y-coordinate, take the y-coordinate of the end point and subtract the y-coordinate of the beginning point. 2 minus 4. For the z-coordinate, take the z-coordinate of the ending point and subtract the z-coordinate of the beginning point. 6 minus 7. Thus we get minus 1, minus 2, minus 1. And we can see this depicted. The point A has coordinates 1, 4, 7, and the point B has coordinates 2, 2, 6. And so this vector AB is the vector going from A to B. And so this is the vector that we have just constructed in this example. We then look at some special unit vectors that we define in R3. Recall a unit vector is a vector with length 1. And we define these vectors as I, j, k. And you'll note that these are extensions of vectors that we defined in two-dimensional space. So I is this unit vector pointing in the direction of the positive x-axis. J is the unit vector pointing in the direction of the positive y-axis. And K is the unit vector pointing in the direction of the positive z-axis. And these give us what we call in linear algebra a mutually orthogonal basis for R3. That's just speak for all of these vectors having right angles between them. These are useful because any vector
can be written, any vector in three-dimensional space can be written as a linear combination of I, j, and k. So for instance, if we have the vector v1, v2, v3, we can rewrite this as v1, 0, 0, plus the vector 0, v2, 0, plus the vector 0, 0, v3. And then we can factor out those vi's. So the first vector can be written as v1 times 1, 0, 0. Then we have v2 times 0, 1, 0. And then we have v3 times 0, 0, 1, which is v1i plus v2j plus v3k. And so this is handy notation that we will use in many different settings to represent vectors in terms of these unit vectors I, j, and k.